So the dot product is an operation that we can perform on two vectors. So it's basically a way to multiply vectors. It's also called the scalar product and the inner product of vectors. So say we have these two vectors a and b and their components. If we took the dot product of a and b, we would get a1 b1 plus a2 b2 plus a3 b3. So you just multiply the corresponding components of the two vectors and then add them all up. So notice that the dot product produces a scalar quantity. The dot product of two vectors is not a vector, it's a scalar. So now that we have the definition of the dot product, we can begin to look at some of its properties. So first, notice what happens when you take the dot product of something and itself. So we're just going to have the sum of the components of the vector squared. And so this is just the magnitude of the vector squared. So something dot itself is equal to its magnitude squared. So next we have the equivalent of the distributive property. So these are all vectors. So b plus c, the components of b plus c are going to be b1 plus c1, b2 plus c2, and so on. And so when we dot that sum with a, we're going to get a1 times b1 plus c1, a2 times b2 plus c2, and so on. And so if we distribute these quantities, we can separate them and see that this is equal to a dot b plus a dot c. So the distributive property holds for the dot product. If we have a dot b, but one of them is multiplied by some constant c, each term in the dot product is going to be multiplied by that c, so we can just factor it out. So it's the same as if we did the dot product and then multiplied the whole thing by c. So we can move constants out of the dot product. And then lastly, we have the commutative property, which is a dot b is the same thing as b dot a, and this should be pretty easy to see from the definition of the dot product. So now we're going to try to find a relationship between the dot product of two vectors and the angle between the two vectors. So before we do this, we're going to quickly review the law of cosines. So remember, the law of cosines says if we have a triangle with sides a, b, and c, and theta is the angle opposite c, then we have c squared is equal to a squared plus b squared minus 2ab cosine theta. So this is what we're going to use to find a relationship. So let's say we draw a triangle with vectors a, b, and then the vector a minus b, because that points from the head of b to the head of a. And then theta is the angle between the vectors a and b. So, well, the sides of this triangle are just the magnitudes of the corresponding vectors. So, if we apply the law of cosines, we will get the magnitude of a minus b squared is equal to the magnitude of a squared plus the magnitude of b squared minus 2ab cosine theta. Now we're just going to simplify the left side of this equation. Remember that if we have the magnitude of a vector squared, it's the same thing as the vector dot product itself. And then we can use the distributive property again. And so a dot a and b dot b are just the magnitudes squared. Simplify this expression. And you can see that we can subtract the magnitude of a squared and the magnitude of b squared from both sides. And then once we do that, we can divide both sides by -2. And so we see that the dot product of a and b is equal to the magnitude of a times the magnitude of b times cosine theta, where theta is the angle between the vectors. And this angle can range from 0 to pi. If theta is 0, that means the vectors are pointing in the same direction. And so the dot product in that case is just the product of their magnitudes. If theta is pi, they're pointing in exact opposite directions, the dot product will be the negative product of their magnitudes. So obviously you can see that the dot product can be a negative number. If the theta is pi halves, then you see that the dot product is equal to 0. If the angle between them is pi halves, then that means the vectors are perpendicular. So we say that if two vectors have a dot product of 0, then the vectors are orthogonal or perpendicular. They're basically the same thing. So you're going to be using this property a lot to test whether two vectors are perpendicular. And also, if we go by this definition, then notice that the 0 vector is orthogonal to everything, because the dot product of 0 and something is always going to be 0. So next we're going to talk about projections. So let's say we have these two vectors a and b. What is the magnitude of a in the direction of b? So that is the length of the highlighted part in the diagram. So just from the diagram, you can see that this is going to be equal to the cosine of theta times the magnitude of a. And so we can get another expression for that. What if we don't know theta? By the equation we found earlier, it's the same thing as the dot product divided by the magnitude of b. This formula tells us how much of a is in the direction of b. And this is also written like this, which means the component of a in the direction of b. This is called the scalar projection because it's a scalar quantity. But what if we want to know the vector projection, which is basically the vector with the length of the scalar projection? So it's the same thing in the diagram, we just add an arrow on the end and it becomes a vector. So well, we already have the magnitude of the vector projection, so all we have to do is get it in the direction of b. And so we can do that by using the unit vector in the direction of b, which is going to be b divided by the magnitude of b. We just have to multiply the scalar projection by this unit vector in order to get the vector projection. But the main thing you're going to be using is the scalar projection. So lastly, we look at another property that comes from this equation. So notice how cosine of theta is always between -1 and 1, which means a dot b is always between, and this is the same thing as saying the absolute value of a dot b is less than or equal to the magnitude of a times the magnitude of b. This is one form of the inequality called the Cauchy Schwarz inequality. This is a pretty famous inequality. You might have to know it sometime.